Okay. So I guess I did my undergrad at the University of Manitoba, computer engineering, and then I went to the University of Toronto to do my grad school, which is where I am now. I'm here where I am today because of Jana. We met back, that girl. We met back at Google. She's like, I think we may need some people to give a talk. I'm like, do you want to come? I'm like, sure, free trip. Okay. So some of this work I presented at a conference, Computer Vision and Pattern Recognition, last year. So this is joint work with my professor, Brendan Fry from the University of Toronto, and Moshe Yoich from Microsoft Research in Redmond, Washington. So I kind of play both fields. So give a background, I guess, of what I've been doing. This is kind of what people call machine learning, which is kind of a subset of artificial intelligence. The idea is that you guys are probably familiar, at least programming and stuff, right? So you can't always just say program something you want to do. Some problems are just too difficult. I guess one example is like spam filtering, okay? There's keywords, maybe you're searching emails and stuff like that, and you want to know if it's spam or not spam. So if an email contains the word Viagra, well, it's probably spam unless you're 60 or something like that. But then spammers try to change it, right? So they replace I with an exclamation mark or something like that. It still kind of looks like Viagra, but it's not. And so you can't just program it like systematically and say, okay, look for the word Viagra, look for the word sex, look for the word whatever, Russian bride. You can't do that. It wouldn't really work. So what you do is you get this collection of emails, and this is what happens. So you've probably heard of Bayesian classifiers and things like that. This is machine learning, one aspect of it. So you get a bunch of emails, and you label them as spam. You label some as not spam. And rather than manually trying to determine what, like, trying to program in a computer, if this, if that, whatever, you basically say, okay, generally speaking, if emails look like spam emails, then label them as spam. If they look like non-spam emails, label them as non-spam. And so you use probabilities, statistics, kind of thing to automatically determine which ones are which. And the computer is actually learning on its own to determine what characterizes spam. And as you have more emails and you label them as spam or not spam, it just becomes, the system becomes smarter. It understands emails and spam more. So there's a lot of other examples of this as well. So face recognition, again, I would challenge you to just sit down and write a program to try to determine, given an image, is this the same person as if I give you another image? It's a really difficult problem. People are still working on this. If I rotate my head, it's a different person. To the computer. Computers are absolutely retarded. They have no idea what's going on. They're the dumbest. They can do things fast, but they're really dumb, right? If I move a little bit and I'm getting to the light differently, totally different person, right? If there's yellow light compared to like sunlight or like blue light or something, completely different, right? It's a really difficult problem. Again, like you can't just program as you would like a database or a web page or something like that, right? It's a different kind of thing. Speech recognition, again, same thing. Everyone speaks differently. People speak faster, people speak slower, different accents. They announce different syllables differently, right? There's all these variations, and there's background noise. Right now it's pretty easy, there's no background noise, but maybe there's music playing in the background. It's really difficult problems. So again, what machine learning tries to do is try to take all these different things. It's not general learning. We're not trying to teach the computer to be a child or anything like that, but it's to solve a particular problem. So what I've done here is I'm basically using these kind of frameworks in order to do some stuff in vision, computer vision, so with videos and stuff like that, and images. Some of my other work has been in computational molecular biology. The reason that they can be so different is that the underlying theory is very much the same. The swimming sides. So with biology stuff, biologists do all these experiments. They have tons and tons of data because they really don't know what's going on. So they just try to measure everything. But then they don't know what to do with it. They're like, we have all this data, but we don't know what it really means. So they're like, okay, we'll try to see what we can get out of it. So things like clustering, classification kind of things. Maybe those are the keywords that you've heard of. Okay, so this topic, I'm going to talk about the video stuff that I've done before. Okay, So this started back in, I guess, 2003. Two of my collaborators, Brendan Fry and Neboshi Yoich, and a student that's in my group, or was in my group, was working on this thing called image epitome. Okay, so essentially what it is it's a miniaturized version of an image. So given this image of this dog here with flowers, background, stuff, and concrete, the image epitome is an image, and it's a smaller representation of it that has a lot of the same features. Okay, so it's not the same, but a lot of the characteristics are the same, right? So there's a bunch of these flowers here, and you see there's kind of smaller representations of flowers here. The idea is that you don't need to represent every single flower. Most of them are pretty much the same, plus or minus a little bit of noise. So why can't we just use a small representation of it, right? So we kind of have the nose because there's not like 3 noses in this image, so you can only have one. But then there's a little bit patch of like concrete here, little bits of fur, some yellow flowers that you can see here. So the idea here is that we can kind of take little pieces of here and just kind of copy and paste them throughout this whole thing to recreate this image, right? That's the wave my hand a lot. That's kind of what is going on, right? So we want this to have a lot of the same features. So they showed some applications in object detection, texture segmentation, image retrieval, compression kind of things. So it's kind of this model that they developed, at least for images, but it's since been used for the motion capture data. They've used it for audio to kind of do a similar thing with audio. And if you believe it or not, some people at Microsoft are using this for HIV vaccine research. The idea there is that they want to make a vaccine for HIV, but targeted to specific DNA sequences. The problem with HIV is that it mutates so much that there's so much variability in the DNA that it's very difficult to really make one single vaccine that will be actually useful, right? So the idea there is that you want to find segments of the DNA sequence that are consistent across all these different strains, and that's kind of what's here, right? You kind of want to say there's tons of crap here, right? But what's really important is that there's kind of this flower shape. There's kind of this like concrete thing, right? So that's what they're kind of doing with the HIV vaccine. So that's pretty interesting stuff. Okay, here's some more examples to kind of get you a better feeling for it. So again, we kind of have, there's all this kind of beige-ish stuff on the wall, and you kind of have these little bits and pieces here as well. Different windows, a lot of them are the same, right? So they kind of get compressed into small little bits and pieces here. There's a bunch of helmets here, and there's kind of just one representative helmet. There's a little bit here, which you can imagine that you can tile around in order to get the outside of this boat here. All the suits, like you can just get little pieces of red and kind of tile them around again. So that's what you kind of have here. There's bits of kind of hats and walls and things like that. So these are kind of cool to look at as well, but this will show that we can actually use this to do some things as well. So another thing is that this is actually circularly wrapped. So as you go along this way, it wraps back onto this way, and as you come up this way, it wraps back onto the bottom. So the reason for that is just you get more efficient use of the space. Kind of cool to look at. So how do we actually learn this? So this is kind of a little bit confusing at first. So what happens is that we start with something that's okay. So what's happening is that the little yellow square on the left is showing kind of one example patch, which we call a patch. And what's happening on the right is it's showing the best match in terms of like Euclidean distance or something like that. And what it's essentially doing, as you can think of, is making that patch on the left, or making the patch on the right look a little bit more like the patch on the left. And you kind of do that for all the patches over here. So essentially what you're doing is you don't tell the computer exactly how to create the epitome. It learns by this iterative process. So it kind of goes in a loop. And what you do is you just kind of make patches in the epitome on the right look more like the patches on the left. And then it comes out. Yeah, I don't want to talk about that too much. Okay, so another way of thinking about this is that this is actually more how you do it. So what you do is you take the input image on the left, and then you basically take all these little rectangular shapes from it, different sizes, big ones, small ones, because they model different features depending on the size of it. So you get this collection of patches over here. And if you did the same thing with the image epitome, the idea is that you want a similar set of patches, a similar distribution over these patches, right? So if you take all these little chunks out of one image, and you take all the little chunks out of this smaller image, if they're the same, then they're modeling the same thing, right? That's the idea. So this is called a generative model. We use probabilistic generative models mostly in our group. So what it really boils down to, so how we actually do the learning is that we start with just a random image, which is shown on the right there. And so it's just kind of sampled from normal distribution and stuff like that. And then you just kind of iterate this process, kind of making the patches in the epitome look more like these patches that we've sampled from the image. And then eventually you kind of get that. Doesn't really go in that manner, but I just kind of simulated it. So what it really boils down to is that there's some math. I don't really want to get into it, I don't think. But you basically just set up probabilities and you want to maximize the probability that the epitome generates the same patches. Okay, so the videos basically do the same thing. So now we stack the video frames together to make a three-dimensional construct. And when we're sampling patches, it's not just different size spatially, but different sizes temporally as well. So sometimes we're grabbing 3 frames, sometimes we're grabbing 5 frames, whatever, right? So if we get these little chunks of video, like really small little chunks of video, and if the video epitome again models these patches well, then it's a small representation that we can potentially use for a bunch of different applications. So there's going to be a little bit more math, which is, so basically what happens is that we set up this probability, it looks really nice, but it's intractable. You can't actually compute it because it's exponential in doing computations. We do these variational approximations, expectation maximization, blah, blah, blah. So basically what we do is that there's ends up being 2 equations, and you just iterate between the 2. You won't understand what they mean, but that's the gist of it. Okay, so video time. So there's a bit of a car, and it's going around this map. Okay, so we want to see what we can do for the video epitome. Okay, so there's not just per se just one video epitome for this, right? There's different ways that you can have it because you can have different sizes of the epitome. So one that you can think of is maybe have the video epitome really small spatially, but really long in time, right? So what happens here is that you get the little snippets of motion that you see through the epitome. So in this one, you can see I've only took 4 frames out of the epitome, which I think was maybe 100 frames, something like that. And in this little bit, you see the car kind of moving to the left, right? In other bits of the video sequence, the car is going around the corner or moving up or whatever like that. But the thing is, you don't need to have every single frame where it's moving across here, right? If you have this one little chunk, that's pretty much enough to cover the entire sequence of when the car is moving along the entire bottom, because it's pretty much all the same, right? You don't need to replicate it multiple times. So another way that we can do it is have the video epitome the same size spatially as the video sequence, but only have 5 frames, right? So these are actually the same size as that, but I have to squeeze it in to fit inside. So what happens here is that because there's only 5 frames to work with, and there's all these different motions, you kind of get them all jam-packed at the same time. What we can kind of see is that we see a little bit of motions of different cars kind of moving around the corner. If you look over here, it's kind of moving along to the right over this way, kind of moving up in other ways. So it kind of puts all the different motions all together in one little thing. So these are kind of cool to look at, see the variability that you'll get in this. But the key thing is that still you get a lot of these same features in here, right? You still see cars moving to the left, you see cars moving up, you see cars moving to the right. That's what we really want to do. But we ultimately really want to use this for something. So talk about reconstruction. So essentially what you can think of is, as I kind of alluded to before, that maybe what we can do is kind of do like what they do They call them code books for compression. So what you do is you replace, if you do, what's it do it? I think Zip might do it. Some of the compression algorithms, what they'll do is that they'll basically define a dictionary of words, and then they do replacements in that, in your initial text file with indexes into this code book. So it's kind of doing this replacement thing for like text compression and things like that. So what we kind of do here is that you kind of take a little chunk here and find the best match in the epitome, like which looks the closest. And then take that part in the epitome and replace the actual pixels in the image with that. Right? So you can imagine that you do this for every single pixel. So basically, reconstruct this image such that all the pixels come from the epitome. And that's what we're calling this reconstruction. So why would we really want to do this aside from doing compression? Let's say that this sign line is actually missing data. So for some reason, these pixels don't exist. If you took a little square around this, right, there's some pixels missing, but you find the best match. You're probably still going to find that it matches best to here, right? Then we can take these pixels that were missing and fill them in here, okay? So that's the idea, that we can do that. We can fill in some of the missing information by partially matching with pixels with the epitome. So maybe we have more missing data. There's missing data everywhere. This is kind of a fake example, but you kind of maybe get the idea that we can maybe do something with this. That we can kind of take little chunks of here, find matches, and do some replacements kind of thing. So basically do something with it. Don't really want to talk about this. So basically do this computational speed improvement kind of thing. The idea is that you can use cumulative sum matrices. So basically every element, it's a matrix such that every element is the sum of all the elements to the left and up of it. And then if you want to compute the sum of all the pixel values in any rectangular shape, you can do it in 4 computations by taking the top left and then adding the bottom right and then subtracting the 2 corners. You kind of have to write it down and then it kind of makes sense. Not a big deal. Sometimes they call it integral imaging kind of things. It's kind of common. But it speeds things up. That's basically what you need to know. More videos. Okay, so this is the first application. Get to more fun things, I guess. So one thing that we kind of looked at was super resolution. So the idea is that you have a low resolution image or video and you want to make it look better, right? You can't just blow it up because it'll look like crap. So let's look at this video sequence for a bit. So there's this plant that was in a parking lot, I guess, and it's a pretty big plant. So if you filmed it really far away, you couldn't really get the details of it. But you can then zoom in and get more of the detail, but you don't get to see the whole thing, right? So can we get both? I want to be able to see the whole plant, but in high resolution, okay? So what we can do in order to do this is, when we've zoomed into this part, learn the video epitome of this, okay? So we learn essentially the high resolution features of the video sequence. And then what we can do is go back to the zoomed out version and do these patch replacements in order to get these high resolution features again, right? So imagine that we have this low resolution video sequence, okay? And when I'm taking little chunks out of here, they're all low res crap. And there's the epitome, which has high resolution features, right? If I can do this matching properly and then take the high resolution features and put them back into the low resolution, then we can recover some of the crisp lines on the plant and things like that, right? So the epitome kind of looks like this. It's kind of, it's an interesting thing to kind of look at. It's kind of mesmerizing sometimes. You kind of see little bits of motion that the plant's kind of moving back and forth. You see kind of the leaves moving here and there. They're kind of, it's mesmerizing sometimes. Okay, so, but we really want to see what happens. Okay, so I took this little chunk here in the white box, is blew it up. So it looks like this. It looks pretty bad. If you do bicubic interpolation, which is what you could do in Photoshop or something like that, you get what's in the middle, right? So it looks reasonable, right? Because it's just basically a blurred representation. But that's all you're ever going to get with it. You're just going to get blurred. So what we do with the epitome stuff is that we're getting the result on the right. So we're getting much crisper lines on the leaves. You get more of the details especially in the branches and things like that. So again, how do we do this? We took the low-res box and we did matching from here. So we took little chunks here, found the best match in the epitome on the far right, and took that chunk, that matching part in the epitome, and did replacements here in order to, did that for all these different patches throughout time in order to get the thing on the far right, which is the super resolution result. So here's a larger result of the same thing. So just to give you a feel for, get a bigger view of it. Okay. So another one that we're doing, which kind of alluded to before, with the missing video. So this is kind of called in-painting, what they do for images. So the motivating concept, I guess, for that was that they had images that maybe were destroyed because of water damage, or people drew ink on it or something like that. And so they wanted to recover these missing bits. So the extension of videos is, okay, there's a car driving, and for some reason there's this artificial box missing. Maybe there was a bird flying there, or there was a fingerprint on the lens or something like that, okay? So the idea now is that let's look at everything that we have in the video sequence, aside from the missing data. Let's learn the epitome of that, because that gives us all the different characteristics, essentially, of the video. And then try to fill in these missing values from the epitome, right? Because if we're filling them in properly, with taking little chunks here where we kind of see the front of the car coming out, we should know that the back of the car follows it, right? So the result ends up being this. So it looks pretty good. Not perfect. It's not fine-tuned in order to do all these adaptations, but it models the characteristics quite well, right? So basically, we're able to fill in these missing values from what the epitome from the epitome that we learned, just from what we could see, and fills it in sensibly. So here's a little bit harder example, because that one the car was just kind of whichever.
Would that process not work very well if the car just turned through that opening?
So yeah, well, what would you think the car was doing? I guess that's the question, right? Well, from what you could see, you pretty much guessed that the car was going straight.
Yeah.
The computer, can't expect things. So basically, I'm telling it, okay, here's what we know about the car, and it kind of does these motions, and it will fill in based on only what it sees. It cannot predict other things. If you had a larger sequence where cars were going this way, right, and there was a part missing, it would fill in that action. But I was only telling it to kind of fill in based on what you expected to happen, right? You would do the same thing, right? If I asked you, you wouldn't guess that it did a swerve. So it does something.
So what if the car made a right-hand turn, like right through that missing data?
Well, it didn't though, because you saw that it was coming out the other.
Yeah,
but if it was doing this, it might have difficulty because it's never seen that motion before. The idea is that I've seen things before, and I can replace the missing values with things I've seen before. So if the car, if you had seen the car do a right-hand turn before, then it would be able to fill it in. It's the same thing as if you have a child, right? Maybe a child that has never seen a car before. If you showed the same thing to them, it wouldn't know what a right-hand turn looks like because it's never seen it before. You obviously have, because you've seen many cars turn right before. So it's the same thing. Basic computers, when they're learning this, they have no prior information, right? They don't have the knowledge that you have, that we all have growing up for years, seeing cars, seeing bicycles. So that's essentially the thing, right? It can only do what it has seen, and I show it very little, right? So that's something sensible, which is what I argue. So here's a more difficult example where there's actually a person walking, so legs are moving and things like that. So it's much more difficult. It's not just the car just kind of going. Okay, so this is maybe a little bit more practical. So there's a fire hydrant in the middle of this, and we want to remove it. Okay, so what we can do is we can consider that those pixels are just missing. We just tell the computer that, okay, these values for some reason we didn't get, so replace it. And I want to see basically the same motion. Again, it can only do what it's seen before. I'm not giving it much of a chance here because it only gets to see about I think 1.5 strides in each way, which each foot in front or something like that. So it's a pretty difficult problem, but it does something reasonable. So I just took the kind of relevant frames here. So it does a decent job. It's not perfect, but the thing here is that this framework is just a general framework. It's more of a model as opposed to just doing the applications. But the Epitome is able to learn these features.
Now, would you get much better results if you had it use a larger Epitome in terms of temporally or spatially or anything like that? Or
yeah,
because you have such limited video, are you sort of limited to the results?
I think it's probably more just the limited video. Like if I saw this extended for a longer period of time and saw more walking, then we'd basically learn all the different invariances, right? So each of these strides are different, right? They don't look very different to us, but to a computer they look dramatically different, right? Just off by a couple pixels can result in a huge error in terms of just doing this matching. But yeah, I think it's more a function of just the amount of data I gave to train. But it does something sensible. Here's another example. This is a bit of a fictitious one, but the results were quite impressive. So what happens here is that each pixel is composed of red, green, and blue values. So what I've done is that for each pixel, for each of the color channels, I just throw away the data with 50% probability. Okay? So the video looks like this. It looks really messed up. You can't really see what's going on. So what's actually happening is that there's the red, green, and blue channels of it, and each value here in each of these, I throw away 50% data. So basically, I have this video sequence, and I throw away half the data, and I'm like, okay, can you recover what the video sequence looked like? Okay, so here's that video sequence again, and this is the Epitome. Looking at it, it's pretty remarkable that you actually start seeing bits of cars and roads and things like that. And you ask yourself, how is this happening? Is it magic? It's not really. Because you can imagine that the computer needs to see all these different versions of basically the same thing, right? It sees multiple versions of the car, but different parts of the data are missing, right? So in one instance, some of the blue channel is missing and some of the green channel is missing. Other times, you get to see the same car, but it's the blue channel that's missing, and you see the red and green, right? So you can kind of overlay these two, kind of combine them in order to cover the channels. Now what we can do, same thing we did before, kind of take patches here, find the best match, and replace what the missing data was. Here's the result. So I think it's pretty impressive that it was able to basically take this with nothing else, right? I'm not telling you to cheat that it knows to try to put red, green, and blue, whatever. Just learn the Epitome of it, and then fill in the missing data, just as we were doing before. Didn't really change anything. Here's the result compared to just Gaussian filter results. So essentially what we do here is that for every single missing value, just take an average of some of the surrounding pixels. So if the missing value is red, just take an average of all the kind of red pixels around it and use that. So the result kind of works. You can see that it works for things that don't move, which kind of makes sense, right? Because the road is pretty smooth and it's pretty uniform. So if you take a pixel here, it kind of looks the same as 5 pixels over, right? So that kind of works out. But things like the moving car, it doesn't reconstruct as well because it's averaging it with the concrete or averaging with other things. So yeah. Another example is that streaming data over the internet. It's a real problem, but it's not a realistic solution because it takes so long to do it. But the setup is that you're watching a video sequence of some newscast or something like that, and because of your internet connection, you're getting drop frames. So you're watching it kind of stalls, and then it plays a little bit more and stalls again, and things like that, right? So it's this missing data problem, right? You're getting these drop frames everywhere, and you want to say, maybe we can fill this in, right? So given just what we see, just the frames that we receive, can we fill in the missing values based on that. And you can do a reasonable job. So if you look at, just watch the left panel, you can kind of see that it just freezes every once in a while, right? And that's kind of annoying when you're watching on the internet. So what you do is you take just the frames that we've received, learn the epitome of that. So again, you kind of get these different characteristics, and it'll interleave the different motions and things like that. So you kind of get continual motion of lips and expressions and things like that. And then use that to reconstruct what the missing values are, which is shown on the right, which is, it's smoother, right? You get to see continual motion of lips and things like that. And eye blinks are continuous kind of thing, right? It's a lot smoother. So there's a bunch of, there's some other work that tries to do this. They're called exemplar-based approaches. They do something similar. Basically kind of try to take chunks and replace, they try to take a chunk here and then replace the missing values with that same chunk. The problem with that is that when you have missing data throughout the whole video sequence, that there's no chunk here that doesn't contain missing values. That's the idea, if you understand that. Yeah, so that's there. So I think that's pretty much close to what I have, and short and sweet. So I just showed you kind of what this whole idea of fitting art is. It's pretty recent work, just a couple years old now. Starting to be used in a couple different areas. It's pretty interesting stuff. So my work was just on the video side and haven't touched it in other domains. But it's not only does it model these different spatial characteristics, texture characteristics, but more importantly, the motion patterns, right? So if it didn't, we wouldn't be able to do all these different applications, which I've shown you here. So the website is here, or you can search for video Vietnamese and you'll get to the website, or you can have the link there. So you're supposed to vote for Jana, I'm told. You're voting for CS She's the one there. I don't know what her responsibilities would be. I'm sure she's a good candidate. And I would vote for her. So yeah, I'll field questions for however long you guys want to stick around.
For something like recovering drop frames, wouldn't it make a lot of sense to calculate the video epitome before transmitting and then send the video epitome along? So this way you have information about what you're trying to recover as well.
Exactly, you can do that as well. There's a lot of different ways. Just the one problem I kind of looked at was more difficult problem, right? You don't have this information, but you can totally do that. You can send basically this compressed version of, these are kind of what features kind of look like beforehand. But on the other hand, if it's like a real-time, imagine that we have really fast computers, like quantum computers. If we have quantum computers, this isn't a problem, which could happen. But if it's like a live newscast, right, and it's sending, you don't have this information beforehand, right? So this, you can do it without any prior information. You can maybe use some of these characteristics for compression as well, basically lossless compression or lossy compression kind of things, where basically if I'm throwing away half the data, I'll have to send you half the data, right? And then if you can recover without any other information, that's pretty good. I haven't looked into it too much though. Yeah.
Couldn't you get around that just by having a bit of lag between?
Yeah, you can for sure. If you want the lag.
So
Maybe you want a real time. Otherwise, like someone's watching the sports game on TV and another person's watching on the computer, and you hear the cheers like 1 minute before you hear the cheers. And like, what? Someone's telling me that they're watching World Cup, and someone's watching, I think, on live TV, and someone's watching on the computer, and they hear, or no, I think they're watching the computer, and then they heard the screams from like a bar across the street, and they're like, what happened? What happened? And they're waiting, and they're like, ah! So, well, sometimes you don't want that delay, right? Or if you're doing like webcamming with someone, right? You don't want a 30-second delay because you say something, then you have to wait an extra 30 seconds before the other person actually hears it.
But would it have to be 30 seconds? Or just
yeah, well, I'm exaggerating. But you want as little latency as possible for those, right? That's more important, I think, than drop frames.
Are there any well-known file formats that use this kind of compression?
No, it's too new for it.
Could this super resolution stuff be used to better, or to make better the like digital zooms on digital cameras?
Yeah, it's totally feasible. Right now, it's kind of researchy still. Like it takes a long time, so we're still doing research to how we can make this faster, maybe hardware acceleration, things like that. But there's a lot of different applications that we can potentially use this for. But again, like this stuff was only like put out in a research conference just last year, right? So usually there's this delay in terms of research into actual product kind of thing. But something's good. Yeah.
How do you go about actually constructing the epitomes here? Are these automatically done by machine, or we just paste in bits of video together?
Oh, it's automatically done. So probably didn't understand the whole learning thing because I just kind of went through it pretty quickly. But the idea is that you kind of take little, so you just take all these different chunks here, right? And I say, okay, imagine I just give you all these little bits and pieces of images, okay? Some of them look the same, okay? So I give you like 100,000 little rectangular pieces, and I say, imagine that you're kind of stitching them together, maybe averaging them in some cases, in order to create a smaller representation, okay? So if I show you little chunks, 50 chunks that all look the same, they're all the same flower, minus a little bit of noise, you would probably just average them together and just have the one thing.
So
right?
throw away all but one of the things all look the same.
Exactly, right.
Just take the
So
rest.
essentially it's doing that exact same thing, except in a rigorous probabilistic framework, so that you maximize the probability that if you were to take little chunks out of here, you'll get the same distribution of patches, right? So again, like for things like if you took this chalkboard or something like that, it's pretty much flat. You don't need the entire thing if I show you all of them, because if I show you like a little chunk of that, they're all going to look the same. So you probably all just put the same thing. So that's how I don't tell it that I want to stitch this together or take little snippets out of here. What happens is that it just learns automatically. So the whole machine learning kind of thing, there's very little that we touch. We give it parameters and things like that, and then it just kind of discovers it on its own. So that's pretty cool.
Now, you said that to start building a video epitome, you started off with an array or a patch of the right size that was, normal random noise or something like that.
Right.
If you start off with, the same parameters, same everything else, with two different distributions of noise, do you get drastically different epitomes and one's more effective than the other, or does the
generally what happens is
randomness?
that you'll get the epitome will look different, right? But different in what sense? Not necessarily. It looks different, but it's not necessarily different. So what happens is that if I took this and just kind of shifted around 10 pixels up, everything shifted around 10 pixels up, it's the exact same epitome, really. The placement of these things in the epitome have no relevance, really. What happens? What's important is obviously the features there that you kind of see cars moving, but also the relative locations of them, so that the car is next to the road or the car is on the road, as opposed to the car is on the grass, because the car was never on the grass, right? So what you'll get is you'll basically get different snippets, but of the same thing. So generally it's not a big issue. It's more the size of the epitome, because the bigger the epitome you have, the more features that you can have, but maybe you get a lot of this redundant stuff and then it's unnecessary, right? So you can imagine that the epitome can be the same size as the image, the video sequence, right? But then what's the point? Because it's the same size. You're not actually doing anything extra. Yeah.
Now, let's say you have two epitomes, one that's really compressed temporally and one that's really compressed in a size map. Can you use the both of them in combination to do the same techniques, super resolution, drop frames, noise removal and things like that? Can you use two different epitomes derived from the same sequence at the same time?
You can probably do something like that, but the idea is that it should be unnecessary. That both should still contain all the same features. So if it's just where you really pull the patch from, right? So when I showed you the small little bits of the car moving, right? You would just take that little chunk and just kind of copy and paste that into the thing. With the bigger one, you just take a small little chunk out of the whole thing, and the idea is that it should be the same thing. It should be the same chunk. So it's kind of redundant to use both, right? If the epitome is learned, is the appropriate size and is the features of the video sequence or the image, then you shouldn't need two, right? If that's the case, your epitome size maybe you should need a little larger epitome kind of thing.
Any other questions? Okay.
On behalf of the Computer Science Society here at the University of Windsor, I present to you a gift.
Oh, thank you.
So excellent. Okay.
Thanks.
Appreciate it.
Thank you. Yeah. Okay. Thanks to everyone for coming out and showing some support. Spread the word of mouth and let everyone know that these things are going on and that they were wonderful, because they were. We'll be having